is receiving the positive pulse, that is from 0 to pi. Diode is getting the positive pulse at the anode side and it is conducting. So during the positive half cycle of the input voltage, the PN junction diode is in forward bias and a load current IL flows through the RL. As a result, the output voltage V0 is developed across the load resistor. So this is the thing for the positive half cycle of the diode. Now as the input voltage Vi increases, the voltage V0 also increases and becomes maximum when Vi is maximum. Later when Vi decreases and goes to 0, V0 also goes to 0. So if you try to see the diagram, the positive potential, the first half you can try to see 0 to pi, we are getting the output. Upper part is the input and what we are getting from the secondary of the transformer, and the lower pulses or lower waveforms are the output from the diode side. Okay, so for the 0 to pi we are getting 0 to pi in that diode side. Then comes pi to 2 pi region. So pi to 2 pi region of the applied input is a negative potential, and this potential what we are giving, what we are applying, what we are giving to the diode, and diode is not going to conduct during this negative potential because negative potential is applied to the anode and diode will be in the reverse bias. In the reverse bias, diode is not flowing, it is a unidirectional device. Hence from pi to 2 pi, if you try to see in the below waveform, we are not getting any output. Then again from 2 pi to 3 pi comes the positive half cycle, and for that positive half cycle we are getting the output from the diode. This is how we can justify that the positive half cycle and the negative half cycle of the given rectifier. See again, if you try to see, however, during the negative half cycle of the input voltage, the PN junction diode is in reverse bias and hence there is no current through the load resistor RL. So here is a very important term related to the rectifier, and here for the half wave rectifier, the diode gets reverse biased during the negative half cycle of the input AC. Hence there is no current through the diode, there is no current flowing through the diode in the reverse bias as we have seen. But at the time when the input reaches maximum value Vm in the negative half cycle, the voltage across the diode also becomes maximum. The maximum voltage is called, that is peak inverse voltage, that should be tolerated, or that should be the ability of the diode to tolerate that negative potential. The peak inverse voltage is a maximum voltage the diode must be able to withstand during the negative half cycle of the input. For a half wave rectifier, the PIV is Vm, maximum voltage, that is Vm. Now comes the full wave rectifier. Half wave rectifier, what is the limitation of half wave rectifier? We are getting the output from 0 to 5, no output, pi to 2 pi, output 2 pi to 3 pi, still then there is no output from 3 pi to 4 pi. These are the output waveforms of the half wave rectifier. Now comes the full wave rectifier. A rectifier which converts complete cycle of the input, that is input AC, is called the full wave rectifier, FWR. There are two types of full wave rectifiers. As we have seen, rectifier is divided into two parts, half wave and full wave. Rectifier, half wave rectifier we have seen. Now the full wave rectifier. Full wave rectifier is again divided into two parts. One is the center tap rectifier, another is the bridge rectifier. Now comes the center tap rectifier. Why it is known as a center tap rectifier? Here the one of the standard transformer which is having tapping at the center of the secondary is used. A center tap rectifier uses a special kind of transformer whose secondary is tapped at the center and the load resistance is connected with it. So if you try to see, there are two diodes, D1 and D2 are connected at the secondary side, and the load RL is connected at the, you can say, at the center tap of the transformer secondary side. There are two diodes, as I have told you, D1 and D2 connected with the secondary. When the current flows through the load resistance, the output voltage V0 is developed across it. See, now we are having the center tap. So upper part is from positive and negative, then after the RL there is a positive and negative. So if you try to see, for the D1 it conducts during the positive half cycle, and during that cycle D1 conducts and D2 is not going to conduct, and during the negative half cycle D2 conducts and D1 is not going to conduct. So for the positive half cycle of the input AC diode, D1 is forward bias and D2 is reverse bias. Hence, a load current IL flows in the upper half of the secondary circuit through the diode D1 and the load resistor RL, which produces an output voltage V0 across the RL. So for the first half cycle from 0 to pi, we are getting the output due to diode D1 and RL. Now for the cycle 2, however, there is no current, as I told you, in the lower half of the secondary circuit, as D2 is in the reverse biased. Now during the negative half cycle, the diode D1 is in the reverse biased and diode D2 is in the forward bias. Hence, so in the negative half cycle, what we are getting? We are getting the output due to the diode D2 and the load resistor RL. And here, as we have seen, diode D1 is in the reverse bias, so D1 is not going to be conducted. These are the, you can say, for working of the diode D1, diode D2 and the waveforms. In the positive half cycle, D1 conducts. So if you try to see the particular waveforms, the first waveform, that is 0 to pi, that is due to the diode D1. Then comes the pi to 2 pi. In pi to 2 pi, the input waveform will give you pi to 2 pi region. We are getting the negative half cycle, and negative half cycle will give you output into D2, then D3 and D4. Thus the current flows through the load during both the half cycles of the input AC in the same direction. Hence, the voltage V0 is developed across the load during the complete cycle of the input AC. Now, here again the peak inverse voltage. As we have seen, what is peak inverse voltage? Peak inverse voltage is the voltage that should be handled by the given diode in the reverse bias. As shown in the figure, D1 is forward bias and D2 is reverse bias. Secondary of the transformer supplies Vm voltage in both the biases, both the halves of the circuit, the upper half and the lower half. The voltage across the load is the Vm, that is the Vm maximum voltage. The total voltage is the summation of voltage across the secondary and the load resistance, and hence PIV for the both cycles equal to Vm plus Vm equal to 2Vm. Now comes the bridge rectifier. So this is the second part, or second, you can say, way to form the full wave rectifier is a bridge rectifier. If you try to see here, we are using 4 diodes in place of 2 diodes. 4 diodes connected in a bridge form, diode 1, diode 2, diode 3 and diode 4, and at the center or diagonally we are connecting the load resistor RL. It is connected with the transformer. Normally step down transformer is used. So the bridge rectifier consists of 4 PN junction diodes connected in 4 arms of the Western bridge, load resistor RL along the diagonal of the bridge. Now again we try to see the pulses or the waveforms applied to the transformer. So first comes the positive half cycle. During the positive half cycle, if you try to see, the diode D2 and diode D4 can conduct the potential. The diode D1 is facing the positive part or positive pulse of the power supply, hence it is in reverse bias, and the diode D3 is getting the negative half, that's why it is in the reverse biased. So for the positive half cycle, that is 0 to pi, what we are getting? We are getting output due to D2, RL and D4, and circuit gets completed. In the negative half cycle, if you try to see the figure what we have drawn, where in negative half cycle diode D2 and diode D4 will remain in reverse bias, and diode D3, RL and D1 will give us the full path for the current. So during the positive half cycle, as I told you, D1 and D3 are in reverse bias. See again into the figure, D1 and D3 in the reverse biased for the positive half cycle. Now again D2 and D4 are forward bias. There will be current IL flowing through the RL, giving rise to the output voltage V0 across it. Now during negative half cycle, for the positive half cycle, D2 and D4 in conducting mode and D1 and D3 in the reverse bias. Now in negative half cycle, D1 and D3 in conducting mode and D2 and D4 will be in the reverse bias mode. So again there will be current IL flowing through the RL, giving rise to the output voltage V0 across it. So this is the complete waveform, output waveform for the bridge rectifier. For the pulse what we are getting for 0 to pi, that is due to diode D2 and D4 what we have seen. Then comes the negative half cycle of the input, which gives us output from pi to 2 pi, that is due to D1 and D3, again D2, D4, D1, D3 and so on. Thus, as shown in the figure, current flows during both the half cycles in the output. During the one half cycle, it is due to diode D1, D2 and D4, and in another half cycle, that is negative half cycle, output due to D1 and D3. Also, the current flows in same direction during both the half cycles. If you try to see, let I show you again. See, the current flowing through resistor RL in both the case is in the same direction. If it is positive half cycle, the path will be like this. Just try to listen. D2 RL D4. This is for the positive half cycle. Now for the negative half cycle, the path is like this. D3 RL and D1. In both the case, just to try to see the current flowing through the RL is in the same direction. That I want to say. Now, also the current flow in the same direction, what we have discussed. Now, why bridge rectifier circuits are preferred? Bridge rectifier circuits are widely used and preferred due to several reasons. What are those reasons? Bridge rectifier does not require a transformer having center tapping type of facility, as we have seen in the case of center tap rectifier. The PIV of diodes used in center tap rectifiers is 2 Vm, whereas in case of bridge rectifier it is only Vm. Such diodes are cheaper. However, the disadvantage of bridge rectifier, if you try to recall, the center tap rectifier was using 2 diodes for the designing purpose, whereas the bridge rectifier is using 4 diodes for its construction. Also, bridge rectifier cannot work properly in low voltage applications because the voltage drop across the 2 forward bias diodes becomes almost 1.4 volt as if we are using silicon diodes. Hence, we may not get the sufficient voltage at the output. Now, how to get the better DC? If you try to recall the block diagram of the rectifier, the first block was the transformer, second block was the rectifier, third block was the filter. Why we are using filter? Because the limitations of the rectifier. Sometimes we are getting, after the conversion from AC into DC, there is a certain AC components available or present with the DC. To remove this DC, we need to use the filter circuit. The function of the filter circuit already we have discussed is to remove the component, AC component present in the output. Now the output of the rectifier is a mixture of AC and DC both. Thus, it is not pure DC, but it is pulsating DC. Pulsating DC, why it is pulsating DC? Because it is having certain AC components and it is right now unwanted. In order to remove these unwanted AC components from the output of a rectifier and to make it smooth, filter circuits are extensively used. Now, there are so many filter circuits available in electronics. Shunt capacitor filter, the technique number 1 for the filtration is the shunt capacitor filter. In this type of filter, a large value of capacitor C is connected in shunt, that is in the parallel with the load resistor RL. The capacitor offers the low reactance path to AC component. Now why it is like this? Let I clear. The capacitive reactance is given by, you can say formula is XC equal to 1 upon 2 pi FC. If it is having the frequency component, it gives you very high resistance, and if it is not having frequency component, that is DC, it gives you very low resistance. The capacitor offers low reactance path to AC component means what? If there is let me try to see the figure. Here is a full wave rectifier. If there is a AC component present in a given output, that those AC components will try to move from that capacitor, because for AC components, capacitor acting as a low resistance device. If you try to recall again the formula, XC equal to 1 upon 2 pi FC. If there is a frequency, higher the frequency, lower the reactance. Now, if you are getting pure DC, where frequency is 0, means what? If you try to place in XC formula F equal to 0, XC becomes almost infinitive. Means what? DC cannot pass through the capacitor, whereas AC can pass easily from the capacitor. Means what? What we are doing? We are passing the unwanted AC component. What we are getting output of the from the output of the full wave rectifier. This is one of the way to remove the SC component of the bridge rectifier or full wave rectifier. Now another way is a series inductor filter. An inductor, the property of inductor is to oppose any change in value of the current flowing through it. This is the nature of the inductor. This property of the conductor of the inductor is used to filter out the SC component present in the output of the rectifier. Any change in the current, that is any SC component change flowing through the inductor can be minimized with the help of this particular inductor. The inductor offers high reactance to the higher frequencies. Now what was the formula for the capacitive reactance? It was the XC equal to 1 upon 2 pi FC. If there is a frequency component, XC decreases. If there is no frequency component, in case of XC is infinite. This is about the XC. Now let me try to see XL. XL, that is inductive reactance. The formula for XL equal to 2 pi FL. Now if there is a frequency, XL and frequency are directly proportional. If there is a frequency, XL is F, as F increases, XL increases. So just try to read this statement. The inductor offers high reactance to high frequencies. XL is proportional to F. So higher harmonic ripples, higher the ripples, it can easy to remove with the help of such type of inductive components. Here is the way how to connect that inductive filter into the circuit. Full wave rectifier in series, there is an inductor and the load resistor. This was the third way. Now the second way, now comes the third way, is a choke input LC filter. What we are using? In first case we have used capacitor alone, then comes the inductor alone, now comes the L and C together with. This filter contributes the feature of both the shunt capacitor and the series inductor. Therefore it performs the filtration more effectively. It consists of series inductor and shunt capacitor with respect to the load. The inductor allows DC component to pass, smoothen out the AC component, however capacitor blocks the DC component, as the formula suggests, XC and XL. This is the basic configuration of the LC type of filter circuit, where inductor is there and the capacitor is there. Then comes the pi filter. In this type of filter, an additional capacitor is used in addition to the LC. If you try to see, first of all we have used capacitor alone, then inductor alone, then the pair L and C, then comes with LC we are again adding the capacitor.